When security students first hear about code review, they often picture a senior engineer scrolling quickly through files and pointing out a few style problems, as if review is mostly about tidiness. For security architecture, manual code review is different because the goal is to verify that high-risk parts of a system behave safely even when the rest of the system is stressed, misused, or changed later. High-risk components are the places where small mistakes can cause large harm, such as identity handling, authorization decisions, sensitive data processing, and the boundaries where untrusted input first enters the system. Interfaces are especially important because they are the doors and hallways of software, and doors and hallways are where attackers like to stand. Manual code review is valuable here because automated tools tend to focus on known patterns, while humans can reason about intent, context, and subtle logic errors. The purpose is not to read every line forever, but to examine the critical flows with enough care that you can say the design promises are actually enforced in implementation. This episode builds a beginner-friendly way to do that without turning review into a political debate or an endless scavenger hunt. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A practical way to start is by understanding what makes a component or interface high risk, because that determines where manual review has the best payoff. Anything that establishes identity, changes privileges, or grants access to sensitive information should be considered high risk because errors there affect the entire system. Anything that crosses a trust boundary is high risk because it is exposed to untrusted input, unexpected sequencing, and misconfiguration. Anything that performs privileged actions, such as changing security settings or approving transactions, is high risk because abuse can be catastrophic even if it happens only once. Interfaces that accept complex input, like structured documents or large payloads, are high risk because parsing and validation mistakes are common. Even internal interfaces can be high risk if the architecture assumes internal traffic is trusted, because that assumption often fails during real incidents. By classifying risk this way, you avoid the beginner mistake of treating every file as equally urgent, which makes review feel impossible. Instead, you focus your attention where the architecture's security posture is most likely to succeed or fail. That focus also makes review less emotional, because you are not judging the whole code base, just the parts that matter most to safety. Before you read code, it helps to define what you are trying to prove about it, because manual review is most effective when it is driven by security behaviors rather than personal preference. For example, you might want to prove that authorization is enforced at the service boundary, not only in the user interface. You might want to prove that sensitive data is filtered and minimized before it is returned to a caller. You might want to prove that privileged actions require explicit permission checks and leave behind reliable audit records. You might want to prove that errors fail safely and do not leak sensitive details. These are behavioral claims that come from the architecture, and manual code review is one way to validate that the implementation actually matches them. When you approach review as proving or disproving claims, you naturally look for control points, decision logic, and boundary handling, rather than getting distracted by formatting. This is also how you keep review constructive, because the conversation becomes about whether a claim holds, not about whether a developer is good. A clear set of behaviors also helps you stop at the right time, because once you have verified the claim across the relevant paths, you do not need to keep reading endlessly. High-risk interfaces deserve early attention because they are where untrusted input becomes internal state, and small validation mistakes can open large attack paths. A good manual review habit is to trace the input path from the interface inward, asking what assumptions the code makes about the input at each step. You look for where input is parsed, where it is validated, where it is normalized, and where it is used to make decisions. Validation is not only about blocking obvious bad values, but also about ensuring that the input matches the expected type, range, and structure, and that it cannot smuggle unexpected meaning into later steps. Normalization matters because the same value can be represented in multiple ways, and inconsistent handling can create bypasses. You also pay attention to whether the interface accepts identifiers that point to internal objects, because that is a commonplace for authorization failures. The key question is whether untrusted input is treated as untrusted until it is proven otherwise, and whether that proof happens before sensitive operations occur. Manual review is strong here because you can reason about sequences, not just about single lines. If validation happens after a sensitive action is already started, that is a design flaw that tools might not catch. Authorization logic is one of the highest value areas for manual review because it is easy to get wrong in subtle ways that still produce correct-looking features. A beginner-friendly approach is to find the function or code path where the system decides whether a caller can perform an action, then verify that the decision happens for every relevant path, not just for the main workflow. You want to confirm that authorization is enforced server-side at the boundary where the action is executed, rather than being implied by client behavior. You also want to confirm that authorization checks use trusted identity information, not identity values supplied by the caller. For example, if a request includes a user identifier, the code should not accept that identifier as proof of ownership without verifying it against the authenticated identity. Another common issue is partial authorization, where the system checks a role but fails to check object ownership, allowing users with the right role to access objects that should be restricted. Manual review looks for these gaps by tracing how identity and object references flow into decision points. When authorization is implemented inconsistently across components, manual review can reveal architectural drift, which is often a deeper problem than any single bug. Identity and session handling are also high risk, and manual review can reveal weaknesses that show up only when you think about attacker behavior and edge cases. You look for where the system establishes identity, how it maintains identity across requests, and how it terminates identity when a session ends or privileges change. A common weakness is assuming that once a user is authenticated, every subsequent action is automatically safe, which can lead to missing reauthorization for sensitive actions. Another weakness is failing to account for role changes, such as a user's permissions being reduced, but their existing session still being treated as if it has old privileges. Manual review helps you notice whether the code checks the current permission state at the time of the action or relies on stale data. You also examine account recovery and password reset logic with extra care, because those flows change identity state and are frequently abused. Even without diving into specific technologies, you can look for the core behaviors. Does the system require strong proof before changing identity-related settings? And does it deny access safely when identity cannot be confirmed? These checks are architecture critical because identity is the root of authorization and accountability. Sensitive data handling is another area where manual review often finds design flaws hidden in otherwise normal code. You want to trace where sensitive data enters the system, where it is stored, how it is transformed, and where it is returned or logged. Data minimization is a key concept here, meaning the system should return only what is needed for the task, not everything it knows. In code, overexposure can look innocent, such as returning an entire object when only 2 fields are required, or logging an error object that contains sensitive content. Manual review helps you notice these because you can connect the data fields to the system's privacy and confidentiality goals. You also check for accidental data mixing, such as combining data from multiple users in one response due to caching or shared state, which can happen if data is stored in global variables or reused across requests incorrectly. Another common issue is inconsistent masking, where some outputs hide sensitive values and others expose them. When you review high-risk data paths, you are verifying that the architecture's promises about confidentiality are enforced by design, not left to chance. This is also where you can spot opportunities to reduce blast radius by ensuring that fewer components ever touch the most sensitive data. Error handling is a surprisingly rich area for manual review because failures are where systems reveal secrets and where security controls can accidentally disappear. You look at what happens when input is invalid, when authorization fails, when dependencies are unavailable, and when unexpected exceptions occur. A secure design expects safe failure, which means the system should deny sensitive actions, maintain consistent state, and avoid exposing internal details to the caller. Manual review can reveal problems like returning overly detailed error messages, failing open by allowing actions when a check cannot be performed, or partially completing a transaction before rejecting it. You also examine whether errors trigger logging that is helpful for investigations without leaking sensitive data into logs. Another subtle issue is that error handling code is often less tested and less reviewed, so it can accumulate risky shortcuts. Manual review helps you treat failure paths as first-class behaviors rather than as afterthoughts. In architecture terms, failure behavior is part of the trust model because attackers intentionally create failures to see what the system does. If the code reveals internal identifiers, stack traces, or configuration details, it may give attackers a map. Catching these issues early protects both confidentiality and the integrity of future incident response. High-risk components often include complex business logic, and manual review is one of the few methods that can catch logic flaws that automated tools struggle to understand. Logic flaws are not always about unsafe functions. They are about the system allowing an action that should not be allowed because the rules are implemented incorrectly. For example, a workflow may require approval before execution, but a code path might execute the action when a certain condition is met, bypassing the approval step. Another workflow might assume separation of duties, but the code may allow the same identity to request and approve. These flaws are easier to spot when you read code with the architecture's intended workflow in mind, tracing state transitions and checking for bypass opportunities. You also look for time of check to time of use gaps, where the system checks a condition, then later uses data assuming the condition is still true, even though it might have changed. While that phrase can sound advanced, the beginner idea is simple. Does the code check permissions and state at the moment it matters, or does it rely on earlier assumptions? Manual review shines here because you can reason about intent and sequence. Interfaces between components are another hotspot because security weaknesses often come from mismatched assumptions across services. When one service calls another, you want to verify that the calling identity is proven, that the receiving service validates that identity, and that the receiving service enforces its own authorization rather than trusting that the caller already did. This is a common design flaw because teams sometimes assume internal calls are safe and skip verification to reduce friction. Manual review helps you look for the actual enforcement point in code, which can be missing even if the architecture diagram claims it exists. If the system uses an application programming interface, API, between services, you examine how requests are formed, what identity information is included, and how the receiver interprets it. You also check whether the interface includes versioning or strict contracts, because loose contracts can lead to unexpected behavior when one side changes. Another risk is overprivileged service identities, where a service can perform actions far beyond its scope, which increases blast radius if that service is compromised. Manual review can reveal where permissions are broad and where fine-grained checks are absent. This kind of review supports architecture quality because it keeps trust boundaries real rather than assumed. Manual code review is also useful for examining how the system uses security-sensitive primitives, such as cryptography, randomness, and secrets handling, because misuse can undermine entire security guarantees. You do not need to be a cryptography expert to review for common architectural red flags, like secrets being embedded in code, sensitive tokens being logged, or weak randomness being used for security decisions. You look for where secrets come from, how they are stored, and whether they are exposed through errors or debugging. You also look for whether encryption is used to protect data in transit and at rest when required, and whether integrity is considered, not just confidentiality. A beginner misunderstanding is thinking that any encryption usage means data is safe, when in reality the details of key management and correct application matter. Manual review can reveal whether keys are handled safely and whether encryption is applied consistently across boundaries. It can also reveal whether cryptography is used in places where it is not appropriate, such as using encryption as a substitute for access control. In architecture, cryptography supports controls, but it does not replace them. Reviewing these patterns helps ensure that security mechanisms are not used as decorative features. Another technique for high-risk manual review is tracing privilege, meaning you follow what an identity is allowed to do across a flow and check whether the code maintains least privilege at each step. You examine whether elevated actions require explicit checks, whether privileges are separated by role, and whether privileged operations are isolated from normal workflows. You also consider whether the code performs actions on behalf of a user in a way that could be abused, such as a background job that executes with high privileges based on user-supplied input. This is a common design flaw because it creates a privilege escalation path. If a user can influence what the privileged job does, they may indirectly perform actions they should not. Manual review can reveal these flows because you can see how user input is passed into privileged contexts. You also look for impersonation patterns, where one component acts as another identity, and you verify whether that is tightly controlled and audited. Privilege review is about ensuring the architecture's trust boundaries are enforced, not just declared. When privilege is handled casually, a small bug becomes a major incident. High-risk manual review helps prevent that by making privilege transitions explicit and controlled. For manual review to be effective and not overwhelming, you need a repeatable way to document findings and connect them to design requirements, because otherwise review becomes a pile of scattered observations. When you find a potential issue, you describe the behavior you observed, the condition that enables it, and the impact if it is abused. You also describe the expected behavior, ideally as a testable requirement, such as enforcing authorization at a specific boundary, denying actions consistently, or minimizing data returned. This keeps the conversation grounded in behavior and helps engineers implement fixes without guessing what you meant. It also helps prioritize, because you can tie findings to sensitive data, privileged actions, and exposed interfaces. A common beginner mistake is writing findings as opinions, like this feels unsafe, rather than as specific observations tied to risk. Specificity reduces politics and accelerates remediation. It also makes it easier to validate fixes later through functional tests and regression checks. In an architecture-driven review culture, manual review findings become inputs to improving patterns, not just tickets to close. That is how you prevent repeating the same mistakes in every code review cycle. Manual code review also benefits from thinking in layers, because high-risk systems rarely fail due to a single missing check, but due to multiple small weaknesses aligning. You ask whether there are multiple layers of protection, such as authentication plus authorization plus data filtering plus logging, and whether any layer is assumed rather than enforced. You also ask whether protections degrade gracefully under failure, because stress conditions are when attackers and accidents both cause the most harm. A layered review does not mean piling on controls everywhere. It means ensuring that when one layer is imperfect, the system still resists catastrophic outcomes. For example, if an input validation mistake exists, authorization and segmentation might still prevent data exposure. If a logging gap exists, strong authorization might still prevent abuse, though investigations would be harder. Manual review can reveal whether layers exist in code paths or whether everything depends on a single fragile assumption. This layered thinking connects directly to architecture because architecture is about distributing trust and control across boundaries. When you review code with layered expectations, you are checking whether the implementation reflects that distribution. It also helps you propose better mitigations because you can choose where to strengthen the system most efficiently. As you practice manual code review techniques for high-risk components and interfaces, the most important habit is keeping the focus on proving security behaviors rather than hunting for clever mistakes. You identify high-risk areas based on trust boundaries, identity, privilege, and sensitive data flows. Then you trace inputs, decisions, and outputs to see whether controls are enforced consistently. You examine authorization logic and workflow integrity because those are common design failure points that automated tools often miss. You pay careful attention to error handling and failure behavior because safe failure is part of a secure design, not a bonus. You review service-to-service interfaces, including API boundaries, to ensure trust is verified rather than assumed and privileges are limited to reduce blast radius. You look for misuse of secrets and cryptography patterns, not as a checklist, but as a way to confirm that security mechanisms support the architecture rather than replacing it. Finally, you document findings as concrete behaviors and testable requirements, so remediation is fast and validation is straightforward. When you can do this calmly and consistently, manual code review becomes one of the most powerful tools for catching runtime risk before it reaches production. and it strengthens the architecture by keeping its security promises grounded in real implementation.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.